Alright, so then we'll get started. So I want to go over a few things before we actually talk about the lecture. I don't know. Yeah, today shouldn't be too long, by the way. This lecture is probably a little longer than, let's say, like, the second lecture. That was really fast, but it shouldn't be too long. Yeah, so today, I don't know. I want the Giants to win, but I don't know. I don't really care, to be honest, but yeah, I want the Giants to win. Because they're old men. I want some old men to do well. Alright, so let's talk about today. So we're going to be doing the fourth lecture, and again, that shouldn't take too long, but it'll be a little longer than the last lecture, which was the beam, most likely. And so first thing, Memo 1 grades. So I still haven't finished, and I'm sorry. I really wanted that to be done by now. I wanted to. Usually, I try to get them done within a week. Obviously, that's not been the case this time around. For whatever reason, it's just been taking a really long time this time. Maybe that's just because I have 3 sections instead of usually 2 for this class. And I'm trying to get, all of these graded at the same time. So all my 3 sections, I want to post the grades at the same time. But I'm close to being done, so it'll be done, either tomorrow or Saturday. So basically, I just need to finish upgrading the discussion section in one of my other classes, and then the abstract section for all of you guys. So I'm close. I'm sorry it's not done yet, but again, it'll be done by either tomorrow or on Saturday. And then the next thing is common mistakes / areas for improvement. So I think I briefly touched on this last class, so in person. But for that, I left some comments on your submission page for Memo 2 for some of, I don't know, like common mistakes or areas for improvement for all of your memos. So again, you can see all of these comments on the submission page for Memo 2. And so take a look at that. And again, I think I talked about some of these kind of in class before we did our lab last week. So one of the things is all figures and tables should have a caption with a number on it. And a lot of these things that I'm talking about, you can see them on the memo template that I have. So let me just go to that in Canvas actually instead. So the memo template, go to modules and then resources. And there's a memo template. Alright. Okay, so let's put this over here. Okay, so figures and tables, they need a caption with a number. So some of you didn't have any captions at all. And some of you, if you did have a caption, you forgot to put a number. So what I mean by that is in my example here for the memo template, so we have table 1. So that's obviously the number. And then we have a short caption there. And then below, your figure or your table, you should have some commentary on that. So you should be interpreting it in some way. So for memo 1, what I recommend here, which is point number 4 here, basically, you would present all of your figures in that first memo. That was, the stress strain curve for all 3 tests. And then you could also maybe present your table 2. And after both of those, you could talk about your graphs and the numeric results that you had. So basically what I wanted to see was some kind of discussion, limited discussion in your results section comparing those graphs. So for looking at the graphs, you could talk about how aluminum was more ductile by looking at the strain at fracture. So, aluminum is going to have a higher strain at fracture because it's more ductile. And you could talk about the percent reduction of area. And then you could also talk about how, I think 1018 steel, that was the strongest. Maybe I mixed it up, 1045 or 1018. They were kind of close. You would talk about that, which one was stiffest. And stuff like that. So limited discussion in your results section, and then you expand upon that in the discussion/conclusion section. Okay, and then references section, I did update this finally. So when I first uploaded this memo template, I didn't have a references section. I think that's just because I reran this in LaTeX on this machine. It's a long kind of ish story, but basically I should have had a references section. And just to give you an example, this is what your references section should look like, something like this. So this one here, that refers to my in-text citation, which is right here. So right there. And for your first memo, that would be an in-text citation for the published values that you had for, the UTS, the yield strength, and the elastic modulus. All right, so that's what the references section should look like. And then the equation editor. So some of you guys, when you typed out equations, you just typed it out kind of, in line, basically. And so you didn't use the equation editor. So like if you had a fraction, maybe you just do inch per inch, which that part is okay if you do it in line. And I mean like you would do like inch per inch if you see in my URL up here. And if you typed in, I don't know, like inches squared, you do it like that. And this is basically what I don't want to see. I don't want to see that little caret there. I actually want you to type out the superscript. So basically, if you're typing out an equation, use the equation editor. It's going to look a lot nicer and more professional. Okay, so do that. I know it takes a little more effort in Word, but I want to see that. Okay, your numeric results. So most of you guys did use a table, which is good. And if you didn't use a table this time around, you weren't like marked down or anything, but a lot of times when you are presenting your results, aside from your figures, of course, it's better to have a table. So for memo 1 again, it would be good to use a table for, showing your UTS, your yield strength, elastic modulus, percent error, percent reduction of area, all of that in a table. But again, if you didn't use a table on this lab, I didn't mark you down because I didn't say you needed one. But it's often, really, it's better to use a table. It's just easier to parse through the results that way. All right, and then in your discussion, so one of the things that you want to start out by for your discussion section is first restating the experiment, and then explaining its relevance or its importance to engineering. So some of you guys, you just didn't talk about this at all. Like you just kind of restated the results right away or something, or only talked about error analysis. But there's a few things you should talk about in this section. So that's listed out in this memo template. It's also on the syllabus. But you just want to make sure that you start out this section by restating the experiment. You don't need to go in depth, right? Just have a little quick explanation for restating what this experiment was and why it's relevant to engineering. So for the first lab, you would focus specifically on tensile loading. So some of you did have examples to real world stuff, which is good, but you want to make sure that you focus on something where tensile loading is the important thing going on. Okay. And then when you restate your important results, so just your most important ones. So in this case, for the first lab, that might be UTS and strain at fracture, so we can compare strength and ductility. And then also, you would, if there was anything where there's a very large percent error, you would mention that again. And that's when you would really kind of dig in and talk about that for your error analysis. Okay, and then also in this section, you're discussing your results, right? So it should be somewhat in depth. This section, I would say, should be about half a page to a full page. If you go past 1 page, it's starting to get kind of long. So especially for memo 1, I would think your discussion and conclusion section should be half a page to a full page. And so again, for that, you're discussing your results, right? So that's when you're kind of digging in a bit. And so you'd be comparing the results in depth. So, which material was the strongest and was that expected? Which one was most ductile? Was that expected? And again, you would restate those numeric results. So basically, you're just going more in depth to what you had in your results section. Okay. So that's it for the kind of comments here. But when you check out your feedback for the first memo, which again, I'll have graded by tomorrow or Saturday. This is here. Yeah, okay. So this is just an example. Obviously, this is not the first memo, but basically what I did when I graded your memo is I have a rubric here. So once it's actually graded, and you might even be able to see some of my comments already. I'm not sure. I tried to set it up so you can't yet, but might not be the case. But once I have everything graded, you can click on your submission for the first memo. You go to I think it's submission details on the actual assignment. And you should get something like this that comes up. And I have a rubric. Okay, so you can see what I kind of was looking for. And you can see the points breakdown. So of course this is just a whole lot of nothing, but I just want to show you what it looks like. So you can see my rubric comments, and I also have comments on your PDF itself. So usually I try to say in the rubric, check out the PDF comments, but I forget sometimes. So basically just make sure you check both the rubric and check your actual PDF on the left-hand side, and you should see some comments that I actually have on the PDF itself. So I don't think I had, well, yeah, you couldn't do this for your second memo, which I know isn't ideal, but really make sure you look at all of my comments, both in the rubric and on the PDF, before you submit your third memo, which is due on the 21st of October. Let me double check that. Yeah, 21st of October, memo 3 is due. Okay, so that's everything, about the memos and the grading for it, the feedback, all of that kind of stuff. Okay, so now we can talk about the fourth experiment. So this is going to be on the column. So far in our lab, our first two tests were doing a attention test. So we did a tension test, same kind of thing. First one, we only used the extensometer and we broke it, right? In the second test, we did a tension test again. We used an extensometer again, but we also used a strain gauge. And we didn't break it that time. We kept it within the elastic range. Third test was the beam. So we had a beam and we applied our two loads down, and that resulted in bending stress and vertical deflection. So that's basically two different tests that we did. We did a tension test and a bending test. And now we're doing a new one, which is going to be a compression test. So we're going to have these different lengths of these kind of hollow columns here. And it's aluminum 6061T6 again. Okay, so we have all of these different lengths here for the columns, and we're going to apply them to a compressive load. And we're going to have, our three different test setups, and each of them, they're going to have different end supports, which we'll be talking about today. So one of them is going to be pin-pin, another is fix-fix, and another one is going to be fix-pin. And these different end supports here, they're going to affect when these columns fail. Okay, so that's what these different fixtures look like. Okay, and then let's see if there's any good pictures here. Okay, so this is a very short column here, and you can see, we have a fixed pin here, and we're going to be applying a compression load or a compressive load, and then we're going to see when it fails. So this is a dial gauge, old school kind of ish one, analog compared to the digital one that you used in your third lab. And we're most likely not going to be using this because this is basically measuring the outward deflection. So once we apply this compressive load, for short columns, it's really hard to measure this deflection because the short columns are going to deflect outwards too much, which we'll talk about too. And basically that just makes measuring that deflection extremely hard, and it's really time consuming, and the data is kind of crap, to be honest, because it's so hard to measure that deflection. So most likely we're not going to measure this deflection in this lab just because it's so hard and so crap. What we will be measuring is basically just the load, and we'll be looking at the load versus this crosshead position, and we'll see what this maximum load is before our column fails. Alright, so that's what it looks like though. Let's see if there's any better ones. Here's a really long rod here, and you can see how much it's going to deflect. Okay, so that's what it looks like. I always like giving you guys a little preview before we actually talk about the theory. Okay, so let's actually go over the lecture now. Have you guys talked about columns in your actual lecture class if you're taking it right now? Columns and or horizontal deflection. Is that a no? A yes? Anything about columns and compressive stress? Okay. Okay, yeah, if you already took it a while ago, you should have talked about it, but if you're taking it now, I'm not sure. Okay, let me pull up my notes here. Okay. Alright, so if you haven't talked about it and you're taking the class now, that's fine. Everything here should give you a good idea of what's going on. Obviously, we're not going to be deriving equations, but we'll be going over everything that you need to know. Okay, I wish my setup here was a little better. I hate looking over. My mic is in the way of my notes, basically. But anyways, let's go over the lecture. Again, this is for the column. We're having a compressive stress on all of these different columns. We're going to take a look at the stress that we have for the compression, and then also we'll talk about the theory behind the deflection that we have, but we're not going to have any equations for the deflection. Okay, so the first thing that we're going to talk about is stability and kind of what that means in context for this lab. Okay, so for our first two labs, again, remember that we had a tension test. So basically, those were stable. So in those two labs, we had tension, and that tension, that tension force, it tends to align along our material. So it's aligning actually along this longitudinal axis, and because that tension force is aligning along that axis, we're stable. But when we have a compressive force, our compressive forces, they tend to, at some point, get misaligned. And because they get misaligned, we have buckling that occurs, that horizontal deflection. And once those compressive forces become misaligned, there's going to be a failure that occurs. Alright, so again we have the tensile force that's kind of aligning along that longitudinal axis. And because of that, the deflection or the deflection is kept at a minimum. Okay, but once we talk about compressive loads, that's going to be different, typically. Alright, so as I always use this ruler, let's see if we can actually see it all. Okay, so imagine that we have loads on the top and the bottom, so we're in compression. So as I'm applying this kind of compressive load, and this is so unstable that I can only apply a very small load, but once I reach a certain load, then this deflects outward, right? So basically, the load on the top and the bottom, those compressive loads, they're getting misaligned at some point, and then it deflects outward. So this failure for this ruler, it's failing, it's a stability failure. So it's not any structural failure, like I haven't exceeded the yield strength of it, but it's failing from stability, and we'll talk about that too. But the main takeaway is that these compressive loading on top and the bottom, they became misaligned along that longitudinal axis, so then we failed. Okay, so that's what you need to know about stability, and again, we can have different columns that either fail from kind of a structural failure because of the yield strength, or we go to the other end when it's failing because of stability failure. And again, we're going to talk about that in more depth as we go on. Okay, so just like we did for the beam, we're actually going to define what a column is. Okay, so this is going to be a long, straight, prismatic bar. And in this case, it's going to be subjected to compressive loads along its longitudinal axis. Okay, and then we're going to have another definition here, which is on buckling. So I might say either buckling or horizontal deflection. So I'll say either or. I kind of interchange them, but basically buckling is horizontal deflection when our column, bends outwards. So let's have let's define that. Okay, so we have buckling. That's going to be a sudden large deformation in our structure due to a slight increase in our loading, in which, before this, there was very little, if any, deformation going on. So we're continuing to increase our load, and at some point, there was a very large increase in deformation. Okay. All right, and something to keep in mind here is that when buckling occurs, that is not material failure, that is stability failure. So just like I showed with the ruler, when that deflected outwards, I said that didn't fail from its kind of structural, strength. It was failing from stability. So if we talk about buckling in this lab, that is stability failure, not structural failure. Alright, so we're going to see this buckling occur for our very long rods. If you remember when we were on VKS, I showed one picture of a pretty long column, and you saw how much it deflected outward. So that rod was failing, or that column I should say really, that column was failing from stability, not material failure. Okay, so we're going to talk about the concept of equilibrium. Kind of quick, just to touch on it, and we're going to relate this concept of equilibrium later on to the maximum load that we have before there's stability failure. Okay, so the first thing I'll draw is a stable system. So all of these different, I'm going to draw basically three different phases here. So I'm going to draw a stable system, an unstable system, and something that is in neutral equilibrium. All right. Okay, so the question, so buckling wouldn't have much to do with our material properties, but with the design. Yeah, not with the material properties itself, but the geometry mostly. So how long it is and what the moment of inertia is. A little bit on the material properties, in this case from the stiffness of it. But we'll get to that later on. So mostly though, buckling is going to occur, for the most part, yes, not because of material properties, but the design. So is it really long and slender? Basically. Okay, so the first one, this is, I don't know, a little abstract, I think, whenever I see this when we talk about these concepts of equilibrium. So the first one, we're going to draw a stable system. Okay, so we have like this little semicircle here, and in the middle, I'm going to draw a ball. Okay, and if I was going to move this ball either to the right or to the left, and I let it go, it would go right back down to the center. It would go back to its original spot. So we're in this kind of state of a stable system. Okay, so I don't know. To me, it seems kind of weird. I don't know, like elementary, but again, if we're moving this ball to the left or the right, it's going to go back to the middle. It's a stable system. If we flip this now, so now we have our semicircle like this. If we have the ball up top here and we move it to the left or the right, of course, it's just going to fall off the side. So now it's going to be an unstable system. Okay, and the main thing that we're going to be talking about is a system that's in this neutral equilibrium. So in this case, we don't have a semicircle anymore. We just have this kind of flat ledge. All right, so we have our ball in the center, and this time if I move it to the left or to the right, then we're just going to move it to the left or the right. So we're not going to go back to the original spot because, we're not on this sloped semicircle. But we're going to change our position, but it's not falling off any ledge. You can imagine this continues on to infinity. But if we move this ball to the left or the right, it's going to move its position, but no basically failure has occurred yet. Okay, and basically the main takeaway, and we'll talk about this right now, is this neutral equilibrium. We are in this state once we reach something called the critical load, when we have our compressive loading on our columns. So we're going to be applying our load. Imagine that it's a long column in this case, just because it's easier to visualize. So we're applying our load. I'll get the old ruler here. So imagine I'm applying the load, and we're okay, and I reach this point called the critical load, where we're neutral equilibrium. So actually, in reality, it's deflecting a little bit. So this is like I move the ball to the left or to the right, but we haven't failed yet. So there's a little bit of deflection, but failure hasn't taken place yet. And then once I go past this critical load, then there's failure. So in this case, it'd be like we have this stability failure from our deflection that's going on, or buckling. Okay, so let's talk about the critical load right now. Okay, so I'm going to call this P and then CR for critical load. Okay, so this is going to be our point of transition from a stable system on the left to unstable in the middle. So it's that transition point when we are in this neutral equilibrium state. So there might be some deflection going on, but we haven't failed yet. So it's that transition point. Okay, so at this point, our load, P, is going to be equal to this critical load, PCR. So all of this is a little abstract so far. We're going to be having equations soon enough. But again, the idea is that at this point, our load is going to be equal to the critical load, which means that we're neither stable or unstable, but we're in this kind of weird limbo state of being in a neutral equilibrium. Alright, so if the load is less than this critical load, then we're stable. Okay, and then if the load is greater than the critical load, we are unstable. So again, if we're thinking about a long column here, it's basically like we have that permanent deformation. We're in plastic deformation where we can't return back to that original state anymore. We're permanently deformed. We're in an unstable system. Okay, so there is an equation for the critical load, but this is only going to apply for long, slender columns, which we still need to define. So, we've been kind of mentioning that there are short columns and long columns. There's also intermediate columns, but we haven't defined what that really means. We need to be explicit about that. We'll do that soon. Okay, so you might see this called either the equation for critical load or the Euler buckling load. Okay, so we have PCR, our critical load. So we're going to skip this derivation. You'll talk about that in your class probably. But we have pi squared multiplied by our stiffness, our elastic modulus, right? And then multiplied by the moment of inertia. And then we're going to divide that by the length squared. Okay, so Michael, this kind of touches on your question, whether buckling depends on material properties. So it does, a little bit, what you would see in your elastic modulus here. But in large part, it depends on the geometry, so the moment of inertia that we have and our length. So a way that you can think about this, if we're looking at this equation for the critical load, if you increase the stiffness, so if you are using a material that is stiffer, then your critical load is going to get higher, which means that it's going to be more stable. So, we need to have a very high load to reach the critical load, basically. Another way you can do that is by increasing the moment of inertia, so we're changing the geometry, or you can decrease the length. So, if we have a short column, then our critical load is going to increase, which means that, if we want to have this column fail, that critical load needs to be really, really high. But if we have a really long column, this is to the power of 2, if we increase that length, then we're going to be affecting our critical load quite a lot, right? So if I have a longer and longer and longer column, the critical load that we have is getting smaller and smaller really, really fast. So that's why you're going to see the long columns in the lab. We're not going to apply very much load on them, but they're already going to fail from, in this case, stability failure. They're going to buckle under very small loadings. But a short column, because it's so short, right, the length is really small, the critical load for those is going to be really, really high, relative to those long columns. Okay, so it is affected by material properties with the stiffness here, but mostly geometry, which you would see from the moment of inertia and the length. But as I said before, this equation, this theoretical equation, is only applicable for long columns. So a short column and a intermediate column, we need different ways or equations to kind of have a guess, basically, when this critical load is going to occur, which we'll talk about. Okay. Okay, so I'm putting long in quotes here because we still haven't defined, what the hell long means, or intermediate or short. So we're going to be doing that in a second. But again, that equation, it's only valid for long columns. Okay. Alright, next thing is going to be the critical stress. Just making sure I covered everything here. Yeah, okay. So critical stress. So we've talked about critical load, right? And we can, use that and divide that critical load by our cross-sectional area to, of course, get stress. Okay, and we're going to call that sigma CR. Sigma, of course, for stress, and CR for critical. Okay, so let's calculate this. So we're going to get our critical load, divide that by the cross-sectional area. And then we're going to get our critical stress. So this is going to be the stress, of course, at the critical load. Remember, the critical load is the point where when we're in this neutral equilibrium. If we go past that critical load, then we're in an unstable system, implying that there's been failure. Alright, so I'm just plugging in here for the critical load and the cross-sectional area. And then we're actually going to rewrite this now into a different form. Okay, so now we're rewriting this to a form of pi squared multiplied by the elastic modulus, all divided by L divided by, I'll probably just have it as a k, but technically it's a kappa. So we have L divided by k squared. And basically we got this k value. Let me write that. So we have, I'm rewriting it to k squared. So we have k squared is equal to our moment of inertia divided by the cross-sectional area. Okay, so that's how we got it into this form. Okay, and this value here, k squared, or you could say, k equals the square root of I divided by a, that's called the radius of gyration. Okay, and something to note here, if you're looking at this radius of gyration, where k equals the square root of I divided by a, all of that is, it's geometric properties. We have our moment of inertia and then our area. Basically, I'm saying that because you want to keep that in mind for the final, which is a long way away, but basically it's, I'll have a question that I like to have, which is how the geometry of our column can affect the stability. So I guess a hint for your final. And we've already talked about that, earlier on when talking about the critical load, how we can increase that by changing either the material property from the stiffness or the geometry, which is the moment of inertia. And now that we're kind of looking at the critical stress specifically, that's going to be the moment of inertia and the cross-sectional area. And still the length as well. Okay, so that's the equation for critical stress right there. And again, this is only valid currently for long, slender columns, because we took this equation from our critical load, which is for long, slender columns. So basically, if you wanted to know what the critical stress was for a long column, again, you can use this equation. Alright, so, why did we rewrite this to be in the bottom in our denominator here? Why is it L divided by k squared? This L divided by k term is called the slenderness ratio, and that's going to be how we can define a short column, or an intermediate column, or a long column. And again, if we look at this, this is all geometric properties here. We have the length, the moment of inertia, and the cross-sectional area. So again, that's going to determine what's a short column, intermediate, or long. So, this is, I guess, just thinking about it now, this is kind of similar to why we convert load and deformation to stress and strain. Okay, because, remember, we converted load and deformation to stress and strain so we could compare materials, right? We could get the material properties regardless of the specific geometry of each of the rods. So if we were doing our first test with a long rod in that case, and we also ran the same test with, using the same material but a short, fat version, let's say, if we ran that test for those two different sizes, basically, for the rod, and we converted it to stress and strain, it doesn't matter. Because we did that conversion, we have the same material properties that we can calculate in the end. And so in this case, when we are defining a short, intermediate, or long, we're not going to use just the, the length of the column. There's more to it than that to define if it's short, intermediate, or long. So it's going to be the length of the column, but also the moment of inertia and the area. So I don't know, maybe it's not the best analogy, but basically, it's more than just the length of the column. It's the length of the column, the moment of inertia, and the area. And we're combining all of those to define whether we have a short column, intermediate, or long. Okay, so a short column So we're going to have a short column if L divided by K, which again is our slenderness ratio. I'll just say SR because I hate slenderness ratio. Too many syllables. Yeah, lazy. Okay, so we're going to have a short column if SR is less than 49.67. Okay, so basically you would, of course, calculate that. You'd plug in, get your length, divide that by I divided by A, and then see what you get. Okay, for an intermediate column, SR, that's going to be in between 49.67. So 49.67 and up to 63. Okay, so that's an intermediate column. Okay, so again, I'm going to call the slenderness ratio SR. Okay, and then a long column. This will be when SR is just greater than 63. Okay, kind of format that better. Alright, so those are the metrics now for when we have a short column, an intermediate column, or a long column. So far we've basically only talked about the long column for the critical load and the critical stress, right? We have a theoretical equation to solve for that. But we don't have anything yet for the intermediate column or the short column. So we'll get to that. Alright, so now what we're going to do is talk about end supports, or the fixed, not fixed supports, sorry. Yeah, the end supports that we have on our system. So there is pin-pin, there is fix-pin, and there's fix-fix, which remember we showed some pictures of that in the beginning of class in VKS. And these different end supports that we have, they are going to affect when failure is going to occur. Alright, so far, our equation up here, the Euler buckling equation, that was derived under the assumption of having end supports of pin-pin. But of course, like we just said, we could have fix-fix or fix-pin, and that's going to change things. Okay, so these end supports, they're going to have a really big effect on when the column is going to fail. All right, I got a lot of notes here, but most of it's kind of not too important, so I'm kind of trying to weed through it. Okay. Alright, so let's say that so far again, our equation for the Euler buckling load and because of that, the critical stress, those equations that we derived earlier, remember they were only for long columns, but even more than that, it was only for a pin-pin support system. Alright, so that seems like really narrow right now. It's not only is it a long column, but it's a long column with pin-pin supports. And it kind of is narrow so far, but we're going to be able to use this concept of what's called effective length, and that's going to give us where we can solve for the critical load and the critical stress for a long column for whether we have a pin-pin end support, fix-fix, or fix-pin. Okay. Alright, so this effective length is going to be the effective length for basically an equivalent pin-pin column. So again, so far we've been deriving these equations for a long column that has pin-pin supports. So the effective length is going to be, let's say we had a fix-fix column. It'll be, this effective length will be the equivalent length of a pin-pin column for this scenario of either a fix-fix end support system or fix-pin. I think that's just like a ton of stuff kind of thrown together in a sentence, so seeing the equations, you'll start to understand what I mean. Alright, so the effective length, we're going to call this L sub E, alright, for equivalent. Okay, so I think that's the most simple definition that we can think of. Technically, there's a little bit more, so I'll state it right now. So the effective length is the length of our equivalent pin-pin column, where the equivalent pin-pin column has the same critical buckling load and same deflected shape as the actual column. So I think the end there just gets too long. Just think of the effective length as the length of an equivalent pin-pin column. Okay, so once we draw out these kind of diagrams here, I think it'll make more sense. I hope so. Okay, so here is a column with pin-pin end supports. And remember, we've had, our equations so far, they were built in with the assumption of a pin-pin column. So in this case, the effective length it's just going to be equal to the length of the column. Okay. And then we can have a fixed pin column. Okay, so we're going to have a pin up top. It could be on top or bottom, it could be flipped. But in this case, I'll put a pin up top. And on the bottom, we have a fixed support. Alright, so now hopefully this makes sense. So here we have a pin fixed column, and its equivalent length is going to be 70% of the length of the column. So 0.7 times L. Okay, so what we're saying here is this pin fixed column, its effective length, or the effective length, it's 70% of a pin column. Okay, so that's it. It's a very simple equation, thankfully. Effective length for a pin fixed column, 0.7 times the length of the actual column. Okay, and then we can have a fixed column as well. Okay, so fixed support on the top and the bottom. And this effective length is going to be 0.5 times L. So the effective length for a fixed column is 50% of the length. Alright, so there we go. So you can already see, you can get an idea of the effects of the end supports that we have on the system. Okay, effective length for a pin column. All of our equations so far were derived with or for a pin column, so the effective length is just the length. For a pin fixed column, we got 70% of the length of this actual column. For fixed, the effective length is 50% of the length for this column. And so we have this effective length now, but if we go back up here to the slenderness ratio, SR, you can see that, this equation, it's the length divided by K, or kappa, the radius of gyration. So we can actually now plug in for this, not using the length, but the effective length. And that's going to, give us whether we have a short, intermediate, or long column. Also for any end support now. So it can be a short column with a fixed end support. Or we can have a column with a fixed end support, and we can see whether it's a short column, intermediate, or long. Okay, up here so far, this was only currently derived for a pin end support setup. But now that we know this concept of effective length, we can solve for that effective length and plug it in here. And same thing with our Euler buckling load equation here and our critical stress equation here. Basically, whenever you see an L, we're going to put L sub E, the effective length. Alright, so let's do that. Okay, so the first one is going to be for the critical load equation, or the Euler buckling load equation. Okay, so this is going to be pi squared multiplied by the stiffness multiplied by the moment of inertia. And this time it'll be divided by the effective length squared. So it's the same equation. We're just now putting L sub V instead of L. Right, and then we can do that for the critical stress as well. Okay, so we have pi squared multiplied by the stiffness, and then we have the slenderness ratio on the bottom. And of course, we're going to put the equivalent length now, divided by kappa, which remember is the moment of inertia divided by the cross-sectional area. And the term in the denominator, of course, is squared. And then the last thing is the slenderness ratio itself. Let's get that. I'm just going to copy and paste it. Okay, cool. Copy. Alright, and then change all of those L's to L sub V for the effective length. And also I want to have a little note up here. These two equations, remember, these theoretical equations here are only valid for long columns. Okay, but since we introduced the concept of effective length, this is for long columns only, but for any end support, so pin-pin, pin-fix, or fix-fix. Okay, we can have all of those. So now we still need to talk about intermediate columns and short columns for how they fail. Alright, so the first one is going to be for intermediate columns, and for that, we don't have any theoretical equations, but we have an empirical equation. So basically it's going to depend on the material that you have. Guess actually let's talk about short columns first, just because it's more simple. So our short columns, they are going to fail by material failure, more specifically by the yield strength. So we're going to be applying load on the short column, and eventually we're going to get to our yield point, or yield strength, and we're going to be entering that permanent plastic deformation phase. So that's why we're going to fail. So short columns, they are going to fail by the yield strength. Long columns are failing by stability failure when they buckle. Okay, so again, short columns are going to fail from yielding. Alright, and so let's say here, material failure. And another way to think about it is they crush. So they aren't buckling, but they're getting crushed. Alright, so there's a beautiful drawing. So you got your column in the beginning, before there's load applied, and then after it's going to crush and get all fat and short, and that's how it's going to fail from the yielding that's occurring. Don't really have any good props for that, but you can imagine this, right? I don't know, like Play-Doh or something. You have this little ball of Play-Doh, or make it a column in this case. Put compression on it, it's going to squish and get all weird. It's like the hydraulic press channel, right? You go to that, you can imagine there's a column, right? And you squish that down and you crush it.
Is it like a soda can?
Oh, yeah, soda can, yeah, like that. Okay, so for us, we're using aluminum 6061 T6 for the columns. So I do have a number here, but I actually think it's a little high. And I looked this up last night, and basically what I saw, just real quick, it said the yield strength for aluminum is at least 35,000 psi. So it wasn't super helpful. But what I have, and I think we were given this on a sheet of paper before from the manufacturer, but I'm not entirely sure. So this is, we'll put a little star next to this right now so we can check it again later. But what I have in my notes is the yield strength for these columns is 39,177 psi. Okay, so I'm putting for our, specifically for us, for our aluminum 6061 T6 columns, the critical stress is equal to the yield stress, which is equal to 39,177 psi. Okay, so I'm going to double check. That's what I have in my notes, so we'll probably use that. But I just say it's high because of what I saw on Google yesterday, but also because in past semesters, I think this number is usually higher, I think, than what happens in the lab. In the lab, when we have our short columns, I think the actual critical stress is lower, a little bit. Not too much, but it's lower. Okay, so we have this for long columns, and we have it for short columns now. For short columns, we don't have, an equation that is taking the effective length into account. All we're saying for short columns is they are going to fail at the yield stress. So it's really nothing fancy here. It's kind of a crude approximation, to be honest. Okay, but we have one more thing to talk about, and that is when our intermediate columns are going to fail. And for that, we have an empirical equation. Okay. Okay. So, I think this is usually given from the manufacturer for the columns that you are given. So, they will fabricate whatever the columns are, and they will run their own tests. And then they will develop an empirical equation so you can predict yourself when you're going to have failure, or when you're going to reach the critical stress. Okay, so again, this is going to be for our aluminum columns that we have for the lab. So we have B minus D multiplied by L sub V divided by K, so our slenderness ratio. I don't know why they have B and D. They're just constants, so let's, I don't know, it seems weird to me, but whatever. B is equal to 38,300. So I guess I could have just already plugged it in, but whatever. Okay, B is 38,300, and D is 202. So those are constants. Okay, they're always going to be like that. And then we have just the slenderness ratio on the end there. So, of course, that's going to depend on the effective length of the column and then the moment of inertia and cross-sectional area. All right, so there you go. So we have formulas for long columns for any end support setup. We have an empirical formula for intermediate columns for any length and end support because of effective length. And then we also have a formula for short columns for essentially any end support setup because we're just using our kind of crude approximation of the critical stress being equal to the yield stress. Alright, so there we go. We got all of our different kind of modes now. So there's one more thing to talk about here, which is going to be a graph. It's going to be a graph of our critical stress against our slenderness ratio. Okay, and this graph is what we're going to be making for the lab. Okay, and this black line, this is going to be the kind of theoretical line that we're going to have. And, you know, experimentally, it's going to look similar. Well, it should. Okay. Alright, so this is what we have. And we're going to have 3 different regions. So we're going to have short columns, intermediate columns, and then long columns. Okay, so we'll say that this region here is going to be for short columns. And so these are going to, the critical stress for short columns, remember, is the yield stress. And if you look at this too, you can see that these short columns, that's the highest amount of critical stress. So, you know, what that is telling us is that the short columns, they need the highest amount of stress before they fail. And as we get longer and longer, there's less and less stress that is required to have them fail. And they're going to fail in different manners, which I'll write down on the bottom too. Okay, the next one is the intermediate columns. Okay, and these are, you know, this curve, we can use our empirical formula that we just saw up here, and then we can plug that in and we can generate this curve. Okay. And at the very end, we have our long columns, which are governed by the Euler buckling load equation, or really plugged in to solve for that critical stress. Alright, so there we go. So just to recap, in the very beginning here, our short columns, we can generate this curve. Really, it's going to be a flat line, so maybe I should have done that because it's the yield stress, right? So it's going to be just a flat line. Let's do it like that. Okay, so flat line because it's yield stress, not a very good approximation, but it's the best that we have. In the middle, we have our intermediate columns, which we can use our empirical formula right here. And this curve, remember, it's just for aluminum 6061 T6 because the yield stress in this empirical formula is specific towards that. And then our Euler equation at the end here for long columns, we have an equation for that Euler developed. So that was pi squared multiplied by E, so that's going to be specific for your material, in this case aluminum, and then divided by our slenderness ratio squared. Alright, so basically what we're going to be doing for the experiment, we're going to test all of these different ranges of columns, and we're going to record the data for what the critical load was for each of them. So we have 12 columns, so what we should have we should have 12 points on this graph. So originally we're going to make this graph ourselves here using all of the equations that we just talked about up top. All of them that I just mentioned. And then we're going to compare that to, like that will be our theoretical curve. And then we're going to use our 12 points that we got from the lab. And we're going to overlay that onto the same graph. And we're going to compare what the curves look like. So I don't know, you might see something like that. It's probably not going to look this smooth, but in pink, if I can actually connect the dots, that's going to be something, that looks like our experimental curve. Alright, so that's what we're doing for the memo. And so the very last thing is how these different columns fail physically. And this will also be something on the final, by the way. I like this lab, even though measuring the deflection is a pain in the ass, which again we probably won't do because it's so hard and just not very accurate. But I think this is it's a pretty cool lab for everything else. So how these columns physically fail, we're gonna have that as a question for the final. So short columns we already talked about, they crush. Okay, they crush like that. I don't know how you draw a crushed column, but whatever. A little blob there. Okay, and that's from yielding. Okay, our long columns 3 are going to fail from stability failure, from buckling. Okay, I know, really nice. Okay, so it's deflecting in the horizontal direction. And again, long columns, they fail from stability failure, not material failure. And then intermediate columns, they're going to be a mix. So it's going to be some crushing and some stability failure, some buckling that's going on. it depends, are you closer to a short column, or are you closer to a long column, or are you kind of dead center in the middle? I don't know how I drew this in the past. I don't know, that's crap. I forget how I did it in the past, but if you just say it's a mix of crushing and buckling, that's good. I don't know how you can really draw that well. Alright, so let me make sure I talked about everything I want to talk about. Yeah. Okay, so I want to mention too before we go, and I should say this once we are doing this lab next week, but when we go into this lab, we got to do everything ourselves. So in the first 3 labs, the load has been applied by the software. But for this lab, we actually need to use the hand controller ourselves to apply these different intervals of loading. So for short columns, at least tentatively, the intervals are going to be in intervals of 75 pounds. Because remember, short columns, they're going to take a higher load until they fail. So we're going to do that in intervals of 75 pounds for short columns. For the intermediate columns, we're going to do that in intervals of 50 pounds. And then for our short columns, we're going to do it in intervals of 10 pounds. And so basically, you're going to get the hand controller, and you're going to use the thumb wheel. And you got to be really careful, because if you used the thumb wheel last class, you shouldn't have needed to. I think one group did though, because they had to reset everything. But once you use the thumb wheel, it's very sensitive still. So even if you're hardly moving it, you can already apply like hundreds of pounds of load onto the material. So you got to be really careful, especially for the long columns, when you're applying 10 pounds of load. You got to barely move that thumb wheel to go by 10 pounds. So again, I'll talk about that before the lab actually starts next class, but I really want to stress that part. You got to be super careful with the hand controller. Alright, and then the equations for kappa, by the way, the moment of inertia divided by A, I'll have that on the deliverables handout as well, so you don't need to, look up the formula. It's not too complicated, but I'll put that on the deliverables handout just so it's convenient. And yeah, so memo 3, that's due next week on the 21st. I will have your first memo grades done either tomorrow or Saturday. I'm obviously aiming to get it done as soon as I can. But make sure you look at the feedback for that from the rubric and the comments on the PDF itself, like I showed in the beginning of class. So take a look at that and make sure you actually use that for your third memo. Because the worst thing is when I put in all this effort, it takes a long time to give all of you guys feedback, and sometimes people don't even take it into account, so you're not going to improve grade-wise too. So make sure you look at the feedback. Really, make sure you look at it. Alright, so that's it for today though. That's the lecture. Next week we're doing experiment 4, so already kind of moving along pretty fast. Alright, so that's it. If you guys have questions, I'll stick around. If not, see you next week. Alright, have a good weekend.
Thank you, Professor.
Thank you, Professor.
Alright, Anthony, you have a question? Alright. No,